So we are mostly talking about ORA. Today is about ORA 4031. So let's see what we can come up with here. Before I do examples, before I show some examples, I just explain you something about shared pool. I'm going to use a view called $KSMP. I just add this here. So these demos, what I do here, don't do this in production. This $X table is dangerous. So there actually are $X, especially this one, which can hang your database. You know, with a plain select query, you can hang your database. So I'll explain why this is, but I use this in my little laptop for demonstrating something about shared pool. So instead of multiple slides and diagrams, I just show you this. So whenever a query $KSMP, this actually stands for kernel service memory management and SP's shared pool. Whenever I query this, then Oracle actually takes the shared pool latches. Nowadays we can have multiple latches. It takes the shared pool latches, it pretty much locks the shared pool that nobody else would allocate or release memory from it, and then it walks through entire shared pool. It scans through the entire shared pool structure, and it will just return me information about every single little chunk of memory in it. So if 1,000 chunks of memory have been allocated from the shared pool, and another 1,000 chunks are free, then I would see 2,000 rows in here. You see, in my database, this shared pool consists of 34,000 chunks of memory. So that's not really too useful information, or not too interesting. What I would really want to know is, I would want to know, are these chunks free or are they used for something? So luckily there is a column called class. So KSMCH class, CLS means kernel service memory chunk class. All right. So when I run it like that, I see the number of chunks of memory in the shared pool, and I see that 6,000 chunks are free. Also 26 more chunks are also free, but they reside in a special area called reserved area. So the reserved area is an area for big allocations. Oracle doesn't let small allocations to allocate memory from there, even if you have a shortage in the main shared pool area. So this is for reducing fragmentation. That if there is not enough free memory in the free lists of shared pool, then if the allocation is big enough, then it's gonna go into this reserved area, which is set aside in shared pool. So how do we know whether a chunk is big enough to be considered big or not? Well, there is a parameter. Shared pool reserved min alloc. So we shouldn't tune it. You know, this is not something we wanna touch. But this just says that the allocation size should be at least 4,400 bytes in order to Oracle's heap manager to go to this reserved area. So basically the whole idea is you want to keep small players, you want to keep small fish separated from the big fish. So that's how everybody fits in there better. You know, you probably know this parameter. So this is the parameter which actually controls how much of space is reserved from the shared pool for these big allocations. So right now in my case it's only 5 megabytes, and actually where this number comes from, it comes from this parameter. So I have set my shared pool size to 100 megs, only, I want to cause trouble. I set it to 100 megs, and this parameter defaults to 5, and which is 5%. And then this just shows that how big is this reserved area is gonna be. So whatever R's you see here, R means that this chunk is actually in this reserved area. All right. So we see that many free chunks. I'll talk about the other chunks shortly, but just knowing how many chunks we have, free, it's not enough, because we don't know whether these chunks are 20 bytes in size or 200 kilobytes each, right? So we actually want to see the size of these chunks. So in addition to count star, I will probably want sum. I want the sum as well. I want to see the total size of a chunk. So you see, this is now in bytes. This is the size of a chunk. And I see that, hey, we have 4 megabytes of free memory in the shared pool. So, so this is a better indication of how much free space we have. I mean, if you look into this that way. But even that is not enough, because sometimes shared pools get fragmented. Or actually, I have to say, shared pools are always fragmented. Whatever, the problem comes from, the fundamental problem comes from the fact that you can allocate different sizes of chunks from the shared pool. If you allocate chunks of 4 kilobytes to 3 kilobytes, 5 kilobytes, and so on, these chunks are not all the same size, and therefore inevitably sometimes you end up with gaps between the chunks, because if you release a 3 kilobyte, if you release or free a 3 kilobyte chunk, this space is going to be free, but you cannot put the 4 kilobyte chunk in there, because there is only 3 kilobytes of continuous space available. So shared pools are inevitably, they are always fragmented, but usually it doesn't cause trouble. Usually nobody notices it because there is enough free space, or when you run out of free space, you can always flush out big enough chunks to create free space. But now if the fragmentation gets worse than it usually is, then you may end up with a situation that you flush out a lot of chunks, but all of these chunks are only 2 or 3 kilobytes. But you want 4 kilobytes. So you may end up flushing out hundreds or thousands of chunks in order to search for a big enough continuous piece of space. Sometimes you flush out 2 chunks which are next to each other, then you can merge these 3 chunks to one bigger chunk. But sometimes that's not enough. So the fragmentation problem shows up when you don't have big enough free slots or space in the shared pool. And you cannot even flush out everything, because even if you do a flush shared pool, then not everything can be flushed out, because these cursors which are currently in use, which are being executed or open, you cannot flush them out because somebody is using them. So even the shared pool flush may not eventually help you. And for that reason, whenever we want to troubleshoot or understand do we have a fragmentation problem or not, we should also look into this. Minimum size of a chunk, it's not that important, but more important is maximum size of a chunk. You see what's going on here. So right now, these are the free chunks. The biggest free chunk is less than 5 kilobytes. So luckily, Oracle for its regular SQL operations, nowadays it doesn't try to allocate 20 kilobytes or 50 kilobytes anymore. 50 kilobytes is a very big number in terms of shared pool allocation sizes. Usually Oracle, takes 4 kilobytes, up to 4 kilobytes. And if your SQL statement requires more, then it just splits this allocation up into smaller pieces for SQL statements. But as I will show soon, for PLSQL things are not that easy. So what we do see from here is that we don't have. You see we have 6,000 free chunks, and the total amount is 4 megabytes. So we have 4 megabytes of free space, but this is only useful for us if we want to allocate up to this amount of space. But the moment we want 5 kilobytes, then we have a problem. We don't have any chunks which are bigger than that. Then we have to make space. Even though we have 4 megabytes of total space, Oracle has to flush out some chunks in hope to find a bigger chunk, or in hope to free a smaller chunk which is just next to some free chunk. So it could coalesce or merge them, and you end up with 6 or 7 kilobytes, and then you take your 5. In my case, let's see what happens here. So obviously you don't want to flush your shared pool in your busy OLTP environment, but sometimes that's used as a quick and dirty workaround. So you see, I flushed the shared pool. You see, now the number of free chunks went smaller. You see, the total space went up. We now have 30 megabytes. We used to have 4 megabytes only. So we have 30 megabytes of free space. So this went up, but for some reason the number of chunks went down. And the reason is exactly as I said. When Oracle detects that there are 2 chunks next to each other which are free, then it merges them. So basically Oracle now flushed out a lot of chunks what it could, and while it was flushing, it realized that, hey, the neighbor of that chunk is also free. So therefore, let's merge it into a bigger chunk. And you see what we get from here is now the biggest chunk is 50 kilobytes. So now we can do allocations up to 50 kilobytes without having to flush anything out. All right. So I'll see if I have any questions which I should answer right away. Okay. Greg asked whether a big execution plan can lead to ORA 4031, and no. So execution plans can also be split into small pieces, 4 kilobyte pieces, starting from Oracle, I think Oracle 10.2 at least, maybe earlier as well. In earlier versions, 9i and so on, you had these issues. Okay. But PLSQL has a problem, and I'll soon demo it to you. Okay, and now I had a few more questions, but I actually intended to explain it next. So first I will take some tea, so I'll be silent for 5 seconds. All right, so far I showed you free chunks, but what are these here? So I'll start with the simplest. Permanent chunks. These are not used for cursors or PLSQL and so on. Permanent chunks are used for permanent allocations. Things like the $V session array, or $V process array, or the transaction array. Things what you allocate during the startup, or sometimes even expand during the runtime, but things what Oracle expects to never to release. So $V session, $V process, and the many other views like that, they are arrays in memory. They actually reside in shared pool, and they are permanent. So they are not flashed out. So they are not like cursors which get flashed out. even if a session logs out, this session slot is not flushed out from memory. The slot is just there, it will wait for reuse. And sometimes Oracle can also pre-allocate memory into this permanent chunk. So I haven't checked it in latest versions, but Steve Adams also wrote in 8 diagrams that when you start up the instance, then Oracle allocates a large chunk of shared pool memory as permanent, just to hide this memory from the regular memory allocations. And the reasoning is that if you have a lot of SQL which is not using bind variables, or if you have a lot of allocations which get allocated and never used again, right? You want them to be thrown away sooner than later. So you don't want them to stay in the cache for a long time. What the trick Oracle did is that it took some percentage of the shared pool, allocated as a permanent one, and then what happened? So whenever you had a lot of chunks which didn't get reused, then when a new allocator came in, they went to free lists, and they saw that, hey, the free lists are empty. There are no free chunks which are big enough. And therefore, these allocators started flushing out these chunks which had been used only once. So Oracle actually keeps track that whether a chunk has been used only once or multiple times. So there is a thing called LRU list in addition to free lists in the shared pool, least recently used list. And this LRU list has transient end and recurrent end. So any chunk which is only pinned twice, first you pin it because you load it into library cache, and second time you pin it because you now want to execute it, right? Any chunk which is only pinned twice is gonna be in the transient end. So any SQL which you only execute once, it's this SQL is gonna be pinned twice. That you load it into cache, that's one pin, and then you execute it, that's another pin. So this is gonna be in a transient end, and these would be the chunks which are first thrown away when there is memory pressure. But if you repin something, if you pin something again, if you execute the statement the second time, then you will have to pin it again. So that's a third pin already. And then once you unpin it, once the execute finishes, Oracle sees, oops, this guy has been pinned 3 times, therefore this is a chunk which is repeatedly used. And it will actually put it into the recurrent end of the LRU list. So what happens is that if you run out of memory in the free lists, then you first start flushing out things in the transient end, just to get rid of these unused things which are not used anymore. And now when you go through the transient list, you flush everything out and you still don't find what you want, big enough chunk. So this is when normally you would have to start flushing out other chunks which are repeatedly used from the recurrent end. But as a little hack here, Oracle actually checks whether there is any hidden permanent memory. So before it starts flushing out these repeatedly used things, it will go and see whether it can take some of this hidden shared pool memory. So that's the general idea. I'm sure things have changed over versions, plus a lot of things have changed now when we can have multiple shared pool subpools. And we'll get there as well pretty soon, I promise. Okay, that was a quite lengthy explanation about the permanent chunks. So the next one is freeable chunks. You see, even though I did a flush shared pool, not everything was flushed out here. And the reason, an important thing to remember here is that freeable does not mean free. Okay, first of all, it's very simple. If something is freeable, then it cannot be free, right? If it was free, then it would be called free, right? So it's not called free, it's called freeable, which means that it's taken by somebody, but it's freeable. And what this freeable means is that this chunk is freeable by the same object which allocated it. So you see, as opposed to recreatable, wrecker means recreatable, which means that anybody can throw away this recreatable chunk. Anybody can flush it out, as long as it's not pinned. Of course, when it's pinned, then somebody is using it right now. You cannot just throw it away. But anybody who allocates memory from shared pool can throw away recreatable chunks. They are kind of, because they are recreatable. You know, chunks like dictionary cache. You can always load your data back from the data dictionary, right? You don't, so therefore dictionary cache is recreatable. Your query execution plans and query text, and these are also recreatable, because you can always rerun your query and it can be always re-optimized. So anybody can throw away recreatable chunks which are not pinned. But freeable chunks can be only thrown away by the same module in Oracle kernel which actually allocated it. So freeable means that I'm allocating it. Yes, I'm gonna free it someday, but it's up to me. It's up to that allocator to decide when it's gonna be freed. It cannot be thrown away by somebody else who is short on memory. And now, if you wonder that if freeable can be flushed out only when the allocator wants, then how come this number went down? We used to have 20 megs here. Now we have 4 megs only. Well, things the rabbit hole goes deeper. By the allocator, I don't mean a session or a user. By the allocator, I mean this kernel module. And sometimes it happens that Oracle allocates a cursor, and it puts the cursor text into a recreatable place. It allocates some other, chunk of memory, which it makes freeable, but it links it to that cursor. So my cursor owns that freeable chunk, but the cursor itself is recreatable. So now when I flush out that cursor, then whatever code path is doing the flushing, it sees that, hey, there is a freeable chunk, and it's owned by that cursor, which I'm gonna flush out anyway, and therefore it's okay to free it. As usual, the rabbit hole goes deeper, so and things change over versions and so on. That's why this whole shared pool thing is so unexpected and hard to troubleshoot. Okay, so much about these internals. Let's see if I have any more questions. So one question that, can we flush pinned objects? No. What actually happens is that when you issue a flush shared pool, or you look for space and you're flushing stuff, then you walk through your linked lists and you see that, hey, there is a chunk which is recreatable. But before flushing it, we will check the chunk header. And if the chunk is pinned, there is a bit in the chunk header which says this chunk is pinned, therefore I cannot flush it. So then I will just skip this chunk. One question, is the LRU in the buffer cache or shared pool as well? Yes, in both. They're totally different things, but buffer cache has a bunch of LRUs. Shared pool has one LRU list per heap. Okay. So I'll get back to some other questions later on. By the way, when we talk about fragmentation, you probably have never heard about fragmentation in buffer cache. Yes, you have heard about fragmentation in shared pool, but never heard about fragmentation in buffer cache. And there is no such thing. And the simple reason is that in buffer cache, you only allocate buffers of the same size. If you have 8 kilobyte block size, then all the buffers in the buffer pool will be 8 kilobyte. You don't have like 9 and 7 kilobytes. This is when the fragmentation is a problem. So you cannot have fragmentation if all your buffers are the same size. And even if you have multiple block sizes in the database, then it just means that you will have to have multiple buffer caches. One buffer cache, or it's called buffer pool actually. One buffer pool is for 8 kilobyte buffers, another one is for 4 kilobyte buffers. And that's what Oracle has tried to do as well since Oracle 10.2. They have tried to normalize some of the chunk sizes. So they try to actually allocate not things like 11 kilobytes, 12 kilobytes, 9 and 8 and so on. They actually always break the allocation down to either 1 kilobyte or 4 kilobyte sizes. So when I run this, all right, so just check how many chunks I have with different sizes. So this is the count and this is the chunk size. So well, this is 10.2. They are not doing that good job here yet. In 11G they have normalized even better. But you see, there is one chunk size is 4 kilobytes, and then even though I have bigger cursors, even though I have cursors which take more space, Oracle breaks it down to this normalized sizes. And this is another. So this is what execution plans usually use, and this is what this cursor heap zeros use. So this is some cursor metadata. So this is the chunk size, and we have 5,000 chunks with that size, kind of normalized sizes. All right. So let's look into some metrics now. Actually, so whenever we have an issue, let me come up with a ORA 4031 now. I failed to do this demo earlier today, but I have to admit that I did prepare a little, and then now I got this demo working. So the guys who watch the video later, they will see it as well. All right. So this is a script that I use for causing hard parses. So basically, I just run a loop, and I just run in this loop. I will just do a select count star, and where row num equals this number. And you see, it's not the bind variable. It's actually a literal variable, and it comes from DBMS random. So basically, I run the same SQL statement again and again and again with just different literal value. All right. Vitsi, että ära grapista enää. Ja mä tean, mä panin mutin päälle. All right. So let's run this. And it takes a parameter how many iterations I want to do. Well, I want to do many iterations. Let's hard parse like hell. All right. One statistic which appeared in Oracle 10.1 or 10.2, which you also see in AWR and StatsPack, is called a SQL area evicted. So this comes from $sysstat or DBA hist when it's AWR, or stats. I think StatsSysstat or something when you query the StatsPack tables. So this is an indication. This is kind of an indicator of shared pool shortage or shared pools pressure. There is a better indicator, but which needs $X access. So, you see, this number goes up because in the other session I'm actually hard parsing a lot, and I'm having a lot of memory allocations going on. So this statistic called SQL area evicted is a good indicator. But what does it mean? It means that somebody has thrown away or thrown an execution plan out of the shared pool. SQL area is the execution plan. And if the memory shortage is even worse, then you probably see this as well, that actually the child cursor metadata, not just the execution plan, but also the metadata about child cursor, like what privileges are needed to run this child cursor, plus its statistics. This will be aged out as well. So if you look into this metric over time, you put it into Excel or something, I'll show you that as well, then that's a kind of a good indicator of seeing whether, how much of stuff with flush out from shared pool. So, okay, so before I will come up with this ORA 4031, I'll just show you I'll show you a statistic. I mean, I'm sure you have seen this in various reports. It's parse count, and this is the hard parse, right? So whenever you soft parse anything, whenever you do a library cache lookup and basically see whether your cursor is in there in the cache, you have a soft parse, and that's the parse count total. And if you do find your cursor and you can reuse it, then that's it. Then hard parse doesn't happen. But if you don't find your cursor, or if you cannot reuse it for some reason, right, then you will also have to do a hard parse. So soft parse always happens, but hard parse will additionally happen when you actually have to compile the cursor again. I use these statistics in my snapper script. So for example, if I do have this cursor evictions going on, and if I do have a lot of parsing, which I see from some AWR report, then I can use snapper like this. I can say, I will say, show the $sesstat statistics. I'm querying $sesstat, not sysstat. Sesstat is session level. Every session has their own stats. And I will say, gather only these statistics. Don't show me wait events and so on, and include only these statistics which contain parse count, or they contain evicted. Right? I can do this. So so this I can do in 10G. On 9i I can use only this like syntax, but in 10G I can use a regular expression. So I can actually do this. In 10G I can say this. It's like a regular expression using Oracle regex. And I say monitor for 5 seconds, do this monitoring exercise only once, and monitor all sessions in the instance. So this will tell me who hard parses the most, and who evicts or flushes out other stuff the most. You see, apparently we have 3 sessions here: 144, 149, 162. And when I look into the numbers here, so H delta means the human readable delta. So it's instead of showing 1,000 as three zeros here, I show K, or M for million if you do millions of logical IOs or whatever. And this column here is normalized to per second. You see, I sampled for 6 seconds actually. I requested 5, but I sampled for 6 seconds. So I see that during that 6 seconds, somebody did that many total parses. I mean, this session here did that many total parses, which is the soft parses. But 8,000 out of these also caused hard parses. And if I divide it by second, I see we did almost 1,500 hard parses per second. And this guy also, evicted, throw out about 1,500 SQL areas or execution plan chunks or heaps, execution plans pretty much from the shared pool. So now I see that this guy is the troublemaker, because this guy only parsed 32 times per second compared to 8,000. It's nothing, right? So so now all I would need to do is just see what this session is doing, perhaps. This seed 149. So I can use snapper or whatever, once you have the seed, you can do anything. You can enable SQL trace and so on. And I can just pick one of the SQLs. So the top SQL is my own PLSQL loop, this script. But actually, if I look into the other SQLs, okay, this guy is already thrown away. So let's do it differently. I know my seed is 149. I can then do select SQL text from $SQL, where SQL ID equals because of all this activity, this old SQL ID, the text for it was already aged out, but this is how I can get these real-time results. And when I see what this guy is running, this session is constantly running this same statement just with a different literal value. So this is a clear case that, hey, I should really use bind variables or one of these Oracle tricks to replace literals on the fly, like this cursor sharing equals force. And this issue probably goes away. I won't have that much of new. I won't have so many new allocations from shared pool. All right. Before I will come up with this ORA 4031, another thing is $KTHLU. So this is the contents of that script. Again, it's part of my script package. So KTHLU. Unfortunately, you need to be sys in order to read it. Oracle doesn't externalize it into a $view. And I only have one sub-pool in this shared pool. So, but this is a useful view which indicates how much activity there is going on in this shared pool. So how much allocation activity and so on. So for example, it tells me how many chunks have been flushed out. So I've even written scripts which collect this data every few minutes, and just you can plot it later on. This is how many times we have moved some chunk around in the LRU list. Basically, when you unpin a chunk, then this will often result in a LRU list move around. And this tells you how many recurrent chunks we have and how many transient chunks we have in this particular heap or subpool of the heap. Okay, and this column tells you how many times we didn't find anything when we flushed out chunks. So basically, Oracle first goes to the free lists where you have completely free chunks. If it doesn't find a big enough chunk from there, then it will start flushing out, evicting existing chunks. And apparently, since the instance was started, this flushing has failed. Basically, we have flushed out everything we could, and we still didn't succeed. And this means ORA 4031s. This means these errors. ORA 4031s. We didn't find from free list. We scanned. This means free unpinned. We tried to free unpinned chunks. We freed them, but we didn't succeed finding a big enough chunk, and we had to return one error. And this tells you the last size of how big this allocation size was, how many bytes we wanted, why we failed. And this error is actually shown somewhere in this error text as well, and it's really important. Because in my case, I immediately see that, hey, this guy wanted over a half a megabyte of memory. That's a really long, that's a really big amount in Oracle, shared pool terms. Usually Oracle plays around with small fish, so to speak. Usually it's half a K, 1 kilobyte, up to 4 kilobytes. So it's really not healthy to constantly release and allocate these big amounts of memory. So what I would do in this case, well, that's clearly a case where I would want to, first of all, I have to find out what is this object, what caused this allocation, and we'll get there as well. But secondly, whatever object it is, I would, if possible, I would want to pin it into shared pool during the instance startup. Because it's better to do these big allocations instantly when you start up, after you start up, when you still have plenty of big free chunks available, as opposed to somewhere later when everything is already fragmented because of all these small allocations. All right. So, and Oracle actually has gone to this reserved area, and it didn't find this big enough chunk from the reserved area, and then it had a miss. Well, and the miss means that I didn't get my chunk. This allocation failed from the reserved area. So this is the last allocation size which caused the failure. This is the maximum ever seen. All right. I've been promising to show you this ORA 4031 error now, and let's do it. All right, so I have a package. So I told you when you run a really long SQL statement, then Oracle breaks it down to 4 kilobyte chunks. In 10G anyway, maybe in earlier versions, I don't remember that anymore. But 9i is ancient anyway, and 8i and so on. But anyway, so this is my package. I'm not using a SQL statement. I'm actually creating a PLSQL package. And it's actually a procedure, not even a package. And you see what the contents are. I just wanted to create a lot of stuff in here. And you see down here, this file itself is 3,700 lines long. And this file itself, with all the white space, it's 4 megabytes long. Sorry, no, it's 400 kilobytes long. Right. So this is a hell of a big PLSQL package or procedure. Well, maybe you already see that, hey, it's probably better to have many different packages or multiple different packages which are smaller instead of one PLSQL package which is 10 megabytes in size. And in newer versions, Oracle actually can split out individual procedures of a package, as far as I understand. But anyway, in this case, this is one single procedure. You cannot really split this up into, or Oracle cannot split this one up into smaller pieces. All right. So before I do it, I just take a quick look into what's going on in here, right? So we have the biggest free chunk is 5 kilobytes only, and the biggest free chunk in this reserved area is 200 kilobytes. So, and now I will run my script. So this will try to create the package. I could actually try to recompile the existing one because I already have a version here. Okay, it's still running. It's probably going to take a long time because you see my parsing script is still working as well. I'm still hard parsing little statements like hell, so I'm competing for the shared pool resources. So I just wanted to see what's the situation here. Apparently, I don't have, or actually you see now the maximum size, the biggest chunk is only 4 kilobytes. So I don't even have, you see now it's a bit bigger. So you see there's constantly some dynamic action happening in the shared pool. So we flush out old things and so on. And you see what happened here. We have an error. Okay, that's interesting. Let's see what is this error. And voila, we actually have an error, ORA 4031. So, and this is what what this session is really about. Now, one of the most important things to look into is, of course, where is this error? Because in this case, it's in shared pool, but sometimes it happens in large pool, in Java pool, streams pool, and whatever heaps we have. It never happens in buffer cache, because buffer cache is not managed by this heap management. It's its own structure. But here we have that, yes, indeed, we have a shared pool issue here. This is how many bytes we wanted to allocate. That's also very important, because right now it's kind of clear that, hey, this issue happened because we wanted so much memory. So if you ever see that you try to allocate 4 kilobytes only, not 500 kilobytes, but only 4 kilobytes, right? This is when you can say that, hey, the share pool is badly fragmented, because you cannot even allocate 4 kilobytes. But if you cannot allocate 500 kilobytes or a megabyte, that's not really a bad fragmentation in the sense that that's sort of a problem with such big allocations. And what you would want to do against these things, these big allocation issues, is well, one thing is just whatever big allocations you have, all these packages, pin them into memory immediately when you start up. So it doesn't give you any performance advantage really. All it gives you is that this package doesn't get aged out, because sometimes you do have packages which are only used every night, for some batch job, or every week once, and then these issues come back every week or every night. But once you pin it into cache, yes, you use more memory, but you won't have these issues. And of course, the large pool reserved area. Oh, sorry, not large pool, but shared pool reserved area. This is the reason. I mean, this reserved area exists for such big allocations. This is why we have the reserved area. It's exactly it's all about separating big fish from the small fish. So and we actually have 5 megabytes of reserved area. So but in my case, I have engineered this whole thing the way that even that's not enough, because there is one more thing to know about Oracle. If Oracle if you have 5 megabytes here, it doesn't mean that you have 5 megabytes of continuous free space in the reserved area. Oracle actually splits it into granules. So depending on your SGA size, things consist, shared pool and then buffer cache and so on. They consist of granules. And in my case, the granule is only 4 megabytes. You see, my shared pool is 100 megs. My granule size, so this is the amount by which you can extend or reduce some buffer cache or shared pool size. The granule size is 4 megabytes. I can actually query this SGA dynamic components. So v$SGA dynamic components, you see this is the shared pool. Its current size is 100 megs, right? and it consists of granules which are 4 megabytes each. So we actually have 25 granules. Shared pool is 100 megs, granule is 4 megabytes, we have 25 granules. And how Oracle allocates this space, it actually takes an equal amount from each granule. So it doesn't take one full granule of 4 megs and another megabyte from another granule. No, it actually splits this allocation reserved area so it spreads it across all the granules. So if I have 5 megabytes to spread around 25 granules, it means that I'll have my brain has stopped working. About 200 kilobytes per granule, right? So I have about 200 kilobytes per granule. So when I start up, yes, Oracle allocates 5 megabytes of reserved area. But you see, well, we actually have 26 free chunks here. Yes, the total is about 5 megabytes. But each of these granules, this 5 megabytes is split into 20, 25 or 26 different physical regions. Therefore, the biggest granule is the biggest free chunk, biggest continuous free chunk in this area is also only 200 kilobytes. So, this is another limitation which I deliberately engineered here. What you would have to do in real life, check the granule size, right? If your SGA is bigger than a gigabyte, or I don't even remember what this threshold was, or 128 megs, I think. It probably is version dependent and so on. If your SGA is bigger, then Oracle uses bigger granules, like 16 megs is a default in bigger SGAs. In some cases, you might want to even change it bigger. But if the granule size is 16 megabytes, then instead of having 26 chunks which are 200 kilobytes each, you would only have less, 4 times less, something like 6-7 free chunks in this area, and each of them would be 800 kilobytes or something like this. All right. So whenever you have an error, look into this. Where did we have the error? And how much space we wanted, how much memory we wanted to allocate. Plus, there is some extra info that what for. You see, the unknown object means that it's not a SQL statement. It's not a SQL statement. Otherwise, we would actually be able to. We could show you the beginning of SQL text as well. But we already see that we want to allocate something from the PLSQL Diana structure and some whatever that means. But we already see we needed that memory for PLSQL. Very good. So whenever you see this, then you can use this KTHLU script. 539,600. You see, this number 1, there used to be number 1 here. So we tried to free a bunch of chunks from the main shared pool area, and we failed. This unsuccessful went up by 1. Plus, then we went to the reserved area, and we also failed. This went up from 1 to 2 again. And apparently this doesn't work. It should show me the last failure size. But because of my earlier test, earlier today, I actually once even tried to allocate a bit more, 40 bytes more than this time. So that shows the maximum size. This should show the last size, but sometimes these things are buggy. All right. So before I look into a trace file, I think we are running out of time as well. I'll show you another script. This is based on an $X table. So there is a table called $X KSMLRU. So I just have a script with this name. So I select from $X KSMLRU. All right. And the $X KSMLRU is a really useful view which shows you who flushed out what and why. So it even shows you this data here even when the ORA 4031 didn't happen, because what usually or often happens is that even before you see the ORA 4031, before that you already see bad performance. So and sometimes you have every week or whenever this issue happens, you have bad performance, high CPU usage, shared pool latch contention, a lot of junk flushed out from shared pool, and everybody complains. So this is when you can look into $X KSMLRU. This shows you that this is like a list of top flushers. And let me just look into the bottom one. So apparently somebody has flushed out 16 chunks. By the way, even before we go there, this doesn't count the chunks flushed out from the transient end of LRU list. Because transient chunks, these ones which are used only once, their SQL statement which is executed only once, that's supposed to be flushed out anyway. So this only counts these chunks which are flushed out from the recurrent end. So we flush out everything from the transient end, we still don't get what we want, then we proceed to the recurrent, frequently used end of the LRU list. And this is when these numbers will be incremented. Oracle, by the way, flushes out 8 chunks at a time and then sees, merges whatever adjacent chunks it finds during this flush, and then sees whether it has enough space, whether it finds a big enough free chunk. If it doesn't, then it takes another 8 and so on. So if you look into this, this is a normal thing to see. For example, somebody flushed out 16 chunks. We wanted to allocate something for this reason. Well, put it into Metalink, you might get lucky and see what it is. Put it into Metalink bug section. This is the allocation size. We wanted to get 4,200 bytes, and this is the beginning of SQL text, and this is the hash value. So I can actually go to $SQL or some historic table and see what is the full SQL text. Or even hash, you can even look into hash if you know how to convert hash values to partial SQL IDs. All right, but basically where I'm getting at is this. It's fine to flush out a few chunks. 100 chunks, it's not so big of a problem either. But you see Oracle lists that somebody has flushed out 4,000 chunks. So that's gotta be a problem, because if you want to flush out 4,000 chunks, you gotta hold the shared pool for quite a long time, and you cannot just throw away the shared pool chunk without notifying the library cache, because you might have a cursor who has an execution plan in a separate chunk, and now you want to flush out that execution plan. You cannot just throw it away. You actually have to go to that cursor as well, to the cursor metadata, and you have to update the pointer. You have to say to that cursor that, hey, I just removed your execution plan. So next time you want to execute this, execute yourself, you have to recreate that plan. So when you flush out things, you won't see only shared pool latch contention. You will actually see library cache latch contention or library cache mutex contention, depending on the version of Oracle. But anyway, this guy is the troublemaker. We flushed out 4,000 chunks because we tried to allocate 500 kilobytes for this some sort of this reason. If you don't know what it is, then put it into Metalink. This is, by the way, the session address. This is the address of the session state object who performed the flush. But the problem with this is that this address, maybe the troublemaker has logged out already or crashed or whatever, and the new session logged on and just reused the same slot at that address. So you cannot be really sure whether the session who is logged on right now here is the one who caused this trouble. Well, what helps is if you look into the logon time to see when this session logged on. Because if the problem happened an hour ago and this session logged on 5 hours ago already, then you know that this session is the troublemaker. All right. So, and see what's going on. So this script is just a select query, as you see. We select from $KSMLRU. I run it again, and you see its contents change. What Oracle does, so this $KSMLRU is a really fun view. It resets its contents to empty when you query it. So this, it keeps like a top list. I think it's top 10. You see, in my case, it seems to be top 10. Top 10 flushers. And if I don't query it for months, then what I see here is the top flusher during this multiple months of time. And the moment I query it, its contents are reset and this top list is built again. It starts from scratch. So you see, the next time I ran it, that the 4,000 went away, and the next, during my query here, or while I was talking, somebody flushed out 80 chunks and so on. So what I've done sometimes to monitor things is something like this. And basically, I sleep something like for 5 minutes, and then I insert more and more. And of course, I insert a timestamp as well. So sometimes when troubleshooting really nasty problems, I've done this. So we troubleshoot, we look into AWRs and whatever numbers, and we cannot pinpoint exactly what's going on yet. But then in order to capture more data next time it happens, we write a bunch of scripts which collect these $X data into a table. So next time the problem happens, you have more data to work on. So it's safe to query this guy. Let me do it this way. $X. So it's safe to query this guy. It's safe to query this guy, but it's not safe to query that guy, because this guy goes through the entire shared pool while holding shared pool latches. And you can hang your database so that even sysdba cannot log on. If you ever have to do this, if you have to query this, then make sure you know the SPID of your process, who is querying it, and log on to that Unix box. And when the hang lasts for longer than desired, then you can do a kill -9 on your process, because 10pmon will clean up after your process and it will release the latches you held. But even sysdba cannot log on when shared pool latch is held for a long time, because every session, including sysdba's one, needs to allocate space in shared pool. Okay, so we did hit this error. I'm going to show you the last thing about the trace file. We did hit this error here, and starting from some version, probably 10G again, there are a bunch of new parameters called 4031 dump bitvec. This is actually a bitmap. I'm not going to convert it to bits or binary, but I'm going to convert it to hex, so it would be a bit perhaps more obvious. So this is a bitmap. And in hex it looks like that. In binary it would look like a bunch of ones and zeros. And every 1 and 0 there has a meaning, that what details to dump out when an ORA 4031 happens. So there should be a note in Metalink, or there probably is information in Metalink about what these bits mean. I have a note somewhere as well. Maybe someday I will publish it if I find it. So basically, but thanks to this mechanism, ORA 4031 dumps are done when you have an error. And Oracle actually has another parameter which kind of protects you from too many dumps. Because if you have 1,000 sessions and now you run out of space, then you don't want all these 1,000 sessions start performing a heap dump. There's the 4031 dump. So actually there are some limits. One limit is that don't do more dumps than once per hour here. Okay. Before this parameter appeared, the solution was something like this. I'll do it with alter session, but you would need to do it with alter system or put it into SP file or init ORA. You probably all know this. This is how you enable SQL trace, for example. You set an event 10046 and you have this extra details here. But equally, you can use this, you can set actions for errors. That whenever an error happens, do something. So basically, whenever 4031 happens, do this. Trace name heap dump level 2. And I don't want, I will just say explicitly lifetime 1. So level 2 is again dangerous in the sense that it takes a heap dump. So it actually, just like that bad $X table or this dangerous $X table here, it actually takes the shared pool latches and walks through the entire shared pool and potentially hangs your instance for seconds or minutes, or if you hit the bug, then for hours or forever, right? But what I do here is that when this error happens, then do a heap dump, level 2, that's the shared pool, and lifetime 1 means that do the heap dump and then turn this event off. I can use like lifetime 10, then it means that whenever you hit this error again and again and again, then during 10 occurrences of that error, do this dump. But I say lifetime 1 here. So at least it kind of it allows us to, well, hopefully you get less dumps that way. But you don't need to use this approach if your database is new enough to have this parameter. So, and you would need to use alter system or put it into init ORA. And next time the issue happens in a session, then this dump is done. However, there is another problem that this, even if you use alter system here, then this lifetime here is session specific. Every session has a lifetime number 1. So actually you still have the risk that if 50 sessions hit the same error at the same time because share pool ran out of space, then you will have 50 heap dumps. So I wouldn't really use that without serious discussion with Oracle support or somebody who's familiar with this share pool stuff. Okay, but anyway, thanks to this parameter, Oracle did dump some information into trace file. You see, this is the trace file. In the beginning, you already said that if you don't want this, if this causes trouble to you and makes the problem worse, then you can set this bit vec to 0, right? Then everything is disabled. All right, and by the way, I'm not going to go through the whole dump. We would need another session for that, but I'll just show you the main thing here. So the same data what you already saw. We wanted to allocate. What's important is that what for and how much space we try to allocate. So did we have a heavy fragmentation issue, or we just requested a way big chunk at the wrong time, or had not configured our shared pool reserved area big enough for our workload? All right. I hope you see the screen. In Metalink, there is actually a note here. There is a note which kind of walks you through from how to read this automatically generated ORA 4031 dump. Apparently, it's available since 9205, so which is nice. So that's kind of covers almost all reasonable databases. I'm sure somebody still runs 7.3 somewhere and they die, but these are usually not this most. These are usually some legacy databases which not that many people care about anymore until they break, of course. All right. So the heap dump, I'm not gonna go much into details. So the heap dump is this. You see, actually, you see these are the Oracle allocates shared pool heap in extents actually as well. So there are things called memory extents, and what you see, this is the address of that extent or the chunk in the extent where it begins from, and the size of it, and you see the status. So apparently we have a chunk which is that many bytes, which is free. There is some other chunk which is used by somebody, but it's freeable by the allocator, and it's used for this reason. So this tells you the reason. What object is it? Like is it a SQL area? Is it some statistics area, and so on. And why I searched here, you see free lists tells you how many free chunks you have. And this shared pool has many free lists, like 254 free lists for very small chunks, a bit bigger chunks, a bit bigger chunks. So whenever you have a chunk which size is 88 bytes up to this size here, it's put under this free list. So that Oracle, if Oracle knows in advance how much memory you need, or whenever you allocate memory, you tell Oracle that, hey, give me 88 bytes. Then Oracle knows that it should start from this bucket where chunks starting from 88 bytes are. There is no reason to go here. You go to this 88, and if you don't find what you want from here, you go to the next size. And if you find a chunk from here, you will split it into what you require plus whatever remains you will put back to this appropriate bucket. So this heap dump, it looks kind of scary, but it's very simple. Its contents just, it shows you a lot of lines with information about which chunk, how big it is, in which location it is, and is it free or not? And if it's not free, then what was it allocated for? So the structure of a heap dump is really simple if you kind of look into that. And I've written a little script which again, you can download as well. It's called Heap Dump Analyzer, which all it does, it just kind of aggregates the contents a bit. All right, I gotta scroll upwards. All right, here it is. So basically, just if you look into that script, you see it's very simple. It just aggregates and sums up some details a bit. So for example, I see that there is in SGA heap, so this is the shared pool heap actually, we have 1,400 chunks which are of that size, and they total this much, right? And they are done for permanent allocations. So all these internal allocations what Oracle uses. So apparently there is some sort of SGA I/O buffer where some I/O is buffered. And I would probably want to search for free if I'm troubleshooting something. I want to see what is the biggest free chunk. So you see, there seems to be one chunk which is almost 4 megabytes, but this chunk itself is not. It's not in the shared pool heap anymore. If you read it like this, so this heap dump has done a recursive dump. So whenever it found another heap inside the shared pool heap, then it went on and dumped that as well, like recursively, or it just went in that. And you see, we have allocated almost 4 megabytes from heap is here, from the shared pool heap. It's a recreatable chunk, and it's probably pinned all the time, I think. And the reason why we allocated, or what for did we allocate it, is this. So we allocated this for this reason, or this is the chunk type. And actually, recursively, the same chunk here, it's dumped out. So basically, we go inside that allocation, and we recognize that, hey, it's another heap. It's actually a heap inside a heap. And we have dumped it as well, and the contents of that heap now are free. But the shared pool manager cannot throw this away, or it cannot use this, because the shared pool doesn't look inside its allocations. All the shared pool manager knows is that it has a recreatable chunk here allocated for this reason. So I just wanted to show that what kind of useful data you would get out from a heap dump file. And I've spoken to Oracle support recently, and the guys behind my Oracle support, and they are actually building a tool which allows you to upload these trace files into Metalink, and then it analyzes it and gets back to you with common with some recommendations. Basically, it checks for common things done wrong, like subpool imbalance and stuff like that, and recommends you something. All right, so I'm over time. Nevertheless, I'm going to show you one more thing. I'm not going to go too much into detail, but I'll show you one more thing. When I query $latch children, since 9.2 onwards, I will actually see that we have 7 shared pool latches. So this is not true anymore, that there is only one shared pool and one shared pool latch. Actually, since 9.2, Oracle can have up to 7 shared pool subpools. And each of these subpools, they are all separate. They're all physically separate from each other. And each of these subpools they are protected by their own latch. So there is actually a parameter which if you search in Metalink, it's mentioned a lot because sometimes people need to modify it. This is the parameter which controls it. It's automatically decided based on the number of CPUs you have and based on the SGA size, or shared pool size actually. In my little laptop it's 1, but if you have like 32 CPUs and more and big enough shared pool, you might actually see 7 there. In my case, I see the same info from here. You see, only 1 latch is heavily used. The other 6 latches are only used when shared pool is resized or initialized. Or I think Flush uses the others as well. But we really only actually use 1 subpool because only 1 latch is used heavily. I just logged onto a different database of mine where this is 4. I've actually manually set it to 4. So this is how many shared pool subheaps we have. And you see, we still have 7 shared pool latches. So this is actually hard-coded into Oracle, but 4 of them are used. So we see that we have 4 subpools. And I just want to, I'm not going to troubleshoot much here, but I just want to show you what this means. For example, when you query $SGA stat, right? I just query only these free chunks. You see, we have that much of free memory in the shared pool. Okay, so 120 megs of free memory. But we don't know how much free memory we have in each subpool. There is a chance that 3 of the subpools are almost empty, and one of them is almost full. And whenever you end up allocating from this one subpool, you get this error. And in 9i days, it was fairly common. So this is why people, if you look into Metalink and search for that parameter, this is why people often set it back to 1. And even nowadays, I've fixed problems in 11G as well by reducing it from 4 to 2 or from 7 to 3 or something like this. So if you don't have heavy shared pool latch contention or heavy SQL without bind variables, then you don't really need that many subpools. So it was introduced for reducing the shared pool latch contention. Because instead of one latch, you would have 7 latches which are all used less. But the problem here is that this we don't know how this free memory breaks down here. But luckily the $X table under this $SGA stat has this info. It actually breaks the usage down. So if you use my script SGA stat X, again it should be in the script zip file with my scripts. It tells you how the space is allocated. So the total space is 300 megabytes. So my shared pool is 300 megs. But you see, this is the breakdown, how different subpools use it. So apparently 3 subpools have gotten 80 megs, but subpool number 4 has had more allocations when the instance started up. And that's why it grabbed more of that free space to itself. Or it grabbed more of that uninitialized space to itself. And as I search for free, now I see how this space has been broken down, and I see that, so this pool has 24 megs of free space, this has 35, 33, and so on. So we don't see too bad imbalance from here. But on the other hand, we don't know how fragmented this free memory is. Perhaps one pool has better fragmentation, other one has worse. So, but anyway, so with multiple subpools, it is possible to see this info. Also, when you use this script, what I showed you earlier it returned only one row. How many flushes we have, how many failures, ORA 4031s. So when you have multiple subpools, you will see that from here as well. So for each subpool, we see the difference, how many flushes we've had, and so on. So if you constantly have this misses here or here, you see this number goes up and up and up, but the other subpools don't have this problem. Well, that's a fair indicator that there is something wrong with this subpool. Or yet another script which tells you who has flushed and how much, for what kind of allocation, and for how big allocation. Then you will see the subpools from here as well. Again, this is the subpool number. If you see the biggest flushes are always in the subpool number 2, always thousands of flushes have been done from subpool number 2, then there may be a subpool issue. Then you would need to go to the SGA stat X script, and first of all check whether all the subpools are roughly at the same size. If they are not, then unfortunately there is nothing you can do other than dynamically increasing the shared pool. But otherwise, when this guy doesn't ever release this memory back on its own. So either you should try to make your shared pool smaller and then bigger again, or just bigger. If you have shared pool problems, then you probably don't want to make it smaller anyway, at least not during the critical production time, because when you make it smaller, a lot of things have to be flushed out, which makes the whole parsing and CPU usage and shared pool latch contention cycle much worse. All right. So this is a script which is based on this dangerous $, and and it's taken from Metalink, and I've modified it a bit to suit my needs better. And you see, I actually say a warning, and now you can press Enter or Control C. I think I had a little formatting issue here. Okay, so I ran this $, KSMP, and this is a script for analyzing fragmentation as well. And I just wanted to show you, it's basically doing the same thing like I showed you in the beginning when I ran this group by on various columns on the $, KSMP. So this script queries the same view. It does the same thing, but it's slightly more pretty and more sophisticated. And you see, if you have multiple sub-pools, then you get this information for each sub-pool. And as I searched for free memory here, I get the list of free memory chunks. So what you see from here is that, well, we have 45 chunks which are bigger than 10 kilobytes in sub-pool number 1, right? So the total space is 14 megs, and the max bytes is what you want. You see, the biggest chunk, the maximum, the biggest chunk, biggest free chunk in this sub-pool is 7 megabytes. So, you know, it's a very big chunk. Here you have even 12 megabytes. So, you know, we definitely don't have a fragmentation issue in these sub-pools. I mean, yes, some of the sub-pool may be fragmented, and that's fine. You know, that's how Oracle heaps work, or that's how any heap works, really. But with variable allocation sizes. But you know, at least we don't have a problem. You know, even if somebody wanted 500 kilobytes, then they still would be able to get it from here, because the biggest free chunk, biggest continuous free chunk is 12 megs. So we don't have a fragmentation problem here. But if I run the same one on my other database where I did have this ORA error, I have to specify what I'm looking for. So I'm looking for free chunks. Right. So you see, in the previous output, we had chunks all the way to 10 kilobytes or sorry, over 10 kilobytes. So because that's already a big size, and you know, some chunks were tens or over 10 megabytes. But here, the biggest chunks are between 4 and 5 kilobytes. Actually, I think there is some measuring error, but they're more like between 3 and 4. I think there is a rounding issue here in this query. But anyway, you see, we don't have two big chunks. So we actually have a chunk which is 4032 only. So we already have like an issue, because if I want 4 kilobytes, 4096 kilobytes, then we would have to flush something out from here. We cannot get 4096 bytes from the free area, because the biggest one is a few bytes smaller. And we cannot allocate 4096 from here either, from the reserved area. Because in order to go and fall back into this reserved area, this allocation size has to be at least that big. So you would get, if you want to allocate 4096 bytes, you go here, you cannot get that much from the free list, then you flush out something, and let's say during the flush you didn't find any bigger chunks either, then you immediately get the ORA 4031. You are not going to go into this bigger area to fragment it further with your little allocations. All right, so I'm only 35 minutes overdue, so it's actually better than last time, and I think in the morning I went 40 minutes over time. So all right, let's see some questions. I only will take a couple of questions. So that's the issue with this free seminars. If you come and attend my troubleshooting seminars, you will actually see slides as well occasionally. Plus, you can ask for more questions. So what is a simulator? So if you see things like simulator LRU and simulator hash ledge, so look into my blog. If you search for something like library cache simulator tunnel podder, I have written a blog entry. So I explain there what it is. So basically simulators are memory structures and some code which is used for remembering which cursors were in memory. And if you remember which cursor was in memory in past, then when you have to reload it and reparse it, then you know that, hey, I'm reparsing something which already was in memory. Therefore, if my shared pool was somewhat bigger, then I wouldn't have to do this reparsing work again, and I would save time. So all the advisors, the library cache, shared pool and buffer cache advisors work on simulators. They just remember what kind of cursors were in memory and which. So when you reload something back, either you reload a buffer from disk to buffer cache, or you reparse a statement which already was in cache, then you know that it was already in memory, but it apparently was flushed out. So these advisors work based on that. So let's see what else. So one question I think is what most of you ask, have in mind. Can you see a recording of this session? So yes, very probably. So my recording still works, or it still hasn't crashed my PC. So I hope that it actually saved the file, and I hope that I can actually upload it somewhere. So yes, there is some 98% chance that you will see the recording. I will blog about it once it's up. I will ignore one question about PGA aggregate target. So it's not related really to shared pool issues. So that's a separate topic, maybe for some other day. So let's see. How do I open the questions? Okay. What else do we have? So I think one very good question is that, okay, what if you actually hit ORA 4031s, and then or maybe you don't see them yet, but you already have this flushing and parsing spikes and so on, and you have shared pool fragmentation, and one of the things which you may want to do as a workaround for reaching at least the evening or weekend to fix it, one of the things is then flushing to shared pool. But flushing shared pool is not really, at some point of time, it may help you the first time or the second time. And in some cases, it may continue to help you, to stay below this critical mass of fragmentation. But sometimes you actually flush, you cause all this parsing trouble, but things don't get better because your shared pool is so full of pinned small chunks which cannot be flushed out anyway, or you have some other a bug or memory leak in the shared pool. So what are the options? How do I keep my server running so I wouldn't have to restart it during the day? And well, the answer number one is just make the shared pool bigger. There is no easy way around it if you already have this problem. Make the shared pool bigger. Maybe don't bump it up by a gigabyte immediately. Maybe add 100 megs per hour, or some amount incrementally until you reach the evening when you can shut down, or the weekend. So I wouldn't just bump it up by a gigabyte. I would just add smaller pieces. you got to do it if your SGA target is already at the SGA max size, right? Then you have to well, just reduce your buffer cache. Or if you don't use SGA target, you still can manually alter the buffer cache smaller and increase the shared pool. Yes, something will go slower because you will have less buffers cached, but at least you won't have these parsing issues for the 31s. But again, if a lot of these issues come from not bad Oracle configuration, but from not using proper cursor management, from not using bind variables. This is how you end up fragmenting your shared pool much faster. You will hit this critical mass much faster than normally. But I have to admit that one of these common issues from Oracle side is these multiple subpools. So this parameter what I showed you, it's actually one of the, over half of the shared pool related issues what I've troubleshooted at the end resolution, or one of these things has been to actually reduce the number of subpools. 7 subpools, I don't see how you need this. And especially when you eventually start using bind variables properly and you don't log on and out for every separate request, then you don't really need the shared pool latches that much at all, because everything you need is already loaded into cache. So one question about the reserved area that doesn't. I mentioned that if the allocation size is small, let's say it's 3 kilobytes, and now you don't find space from the main shared pool area, then if the allocation is 3 kilobytes, it's not going to try to allocate this 3 kilobytes from the reserved area, because then it would mess up the reserved area even more. But if the allocation is bigger than this parameter specified, this minimum allocation size, then it will try to go to reserve area if it doesn't find what it wants from the main shared pool. Okay, because if you do let these small allocations into reserved pool, there is a chance that you cannot get them out of there anymore because they are pinned. And then maybe all your tens of megabytes of the reserved area are unusable for the large allocations, because every now and then, or every here and there, every location here and there, you have this little fish or small fish who blocks the space for a bigger one. One question that should you flush the shared pool at least 3 times in order so that it would work well because of dependencies. And the reason is not dependencies, because when you flush something out, so the dependencies, I don't think this is the reason. So you can have a table definition or some sort of view definition in library cache, and now a SQL depends on it. If you reach that, so if this SQL is unpinned, then you can throw it away. If you reach that SQL, you can flush out this SQL, and once you arrive to the view definition in library cache or that object, you can flush it out as well. And if it's the other way around, if you first arrive at the view definition, then you can still throw it away, because you will walk the dependencies. You will see that, okay, I wanna throw away this view definition, and oops, I cannot throw it away because somebody depends on me. But then you can walk the dependencies and see who depends on me. So and you see that, hey, there is a SQL which depends on me, which is unpinned, and I can flush it out. So this is doable thanks to the dependency list, but I have to admit I'm not fully sure whether Oracle actually does it. So there may be something there that perhaps if a chunk is used by other objects in library cache, it has dependencies, perhaps Oracle just bails out and doesn't flush it out. But I have to guess here. I would guess that Oracle actually does walk the dependencies because you want to flush out everything. But I think the bigger reason is that if you constantly execute cursors, then if you do a shared pool flush, then at first time some of these executions or some of these objects may be not flushed out because they happened to be pinned at the time. So when you run another flush after that immediately, then perhaps these chunks which were pinned 3 seconds ago, they are not pinned anymore, and you can flush them out as well, and therefore opening up a better chance to coalesce free chunks into bigger ones. So yes, when I want to, I think, long story short, when I want to have this emergency workaround and desperate workaround, and I have flushed the shared pool, I usually have flushed it twice. Not so more than once, but twice, or you can just try 3 as well. Unfortunately, it's not easy to test this kind of thing because you don't want to test this out in your production environment. And if you run a little benchmark in test environment, it may not represent the reality. So when I showed you Snapper, let's see if we see this. So one more question is that I showed you that there is a parse count. This is the soft parses, and if soft parse always happens anyway, and if so this goes up anyway if you do parse, if you open a cursor and parse. And hard parse additionally happens. It happens as well if you don't find your cursor from cache. But the question was that what about if the cursor is in cursor cache? So as Tom Kite has said, when the cursor cache, when your statement is in a cursor cache, then a softer soft parse happens. You still have a soft parse, but it's softer, and the reason is that cursor cache already keeps the library cache lock in place and pointers to the actual physical location of the cursor. So soft parse means that you have to do a library cache lookup because you don't know where your cursor physically is. But the softer soft parse, thanks to the cursor cache, doesn't have to do a library cache lookup. It doesn't have to walk through the library cache, hash tables, because the pointers to the physical location of the cursor are in place. And now there is a question that is there a statistic which shows that whether you had a softer soft parse or not? And yes, there is. So session cursor cache hits. So when you run Snapper on a session, well, let's run it. I'm ridiculously over time anyway, so what the hell. I'm gonna run lots of soft parses. So lots of soft parses is another loop which just parses the same statement all over again. So let me just use a new session. So it just parses the same statement, so it should be a lot of soft parses and a lot of cursor cache hits. So my seed is 149. Let's run Snapper on it. I'm actually lazy. I have a shortcut called SN which runs Snapper for me with these options you see there. No, okay, so I think this gets even better because in this case, you see we have a lot of recursive calls and a lot of executes. So we execute 34,000 times. So this is because, this is my PLSQL loop which executes the same cursor. But PLSQL actually keeps cursors open. So PLSQL has a further optimization. So it uses its own cursor cache. So it actually keeps the cursor open. So we don't see this statistic from here. But I can just do this. Let's just run a new test. You see, I run this multiple times, and let's see. I run Snapper. All right, so Snapper runs for 5 seconds. I will run this guy once. So now we should have a parse and so on. See how many stats were incremented, including SQLnet, SQLnet round trips and so on. Snapper shows you these stats which changed. It doesn't show you these stats which were zero, which didn't change during this 5 seconds. Every session has over 600 different stats, by the way. So that's a gold mine. This says that. All right. Anyway, so we see a parse count. We only did one parse during this time. We don't see parse count hard anywhere, so therefore we didn't do any hard parses. And we also see that the session cursor cache hit is 1. So we had one soft parse, but it happened to be the softer soft parse because we had a cursor cache hit. So this is how you know that the softer soft parse happened. So next time if you see that the parse count was 10, but cursor cache hits was 5, then you know that 5 soft parses actually resulted in the library cache lookup as well. But the other 5 were session cursor cache hits. So basically you found the existing cursor, it's already open actually from your cursor cache in UGA, and you could follow the pointers directly to the physical location of the cursor in the shared pool. All right. I think I'll take one more question and then we gotta finish. I'm sure some people have work to do as well here, and then we'll wrap it. One question was that, let's see. One question was that, I think this is like a topic for some other day, but nowadays you can have buffer cache inside shared pool, right? So you heard it right. Nowadays you can have buffer cache inside shared pool. Google buffer cache inside shared pool, right? If you Google for that, you will end up in my blog and you will see this article. And actually you can have it in streams pool as well, as it turned out later. So if you look into the second article, and that's a good article for finishing up actually. So next time when you look into SGA stat and you see KTHLU access, so that for some reason somebody takes 10 megabytes from my shared pool for KTHLU access, then read this article further. I have evidence or proof which shows that this memory inside shared pool is actually part of buffer cache. So this memory is used by these buffers, for example. So this is the block number, file number, block number, and object ID. And the reason this is needed for SGA target, it's needed for automatically, or it's needed for reducing shared pool size if needed. So, well, you can read about that yourself. Okay, so I could go on for another 4 hours, but I think that's enough. I hope that this recording will turn out well, and I will try to upload it somewhere. Thanks for attending this session. We had like almost 200 people, I think, logged on to this one, so it's really awesome. I think I'll be doing more of these sessions. So check out my blog, check out my awesome seminars where you actually can ask questions with voice and get almost all your questions answered. And stay tuned. I will probably do more of these events in the near future. Thanks very much, and I'm gonna log out now. Bye.